the last session in this room is how do we adapt to changing conditions. And Taras Lychik and Alan Moulin are both with Agriculture and Agri-Food Canada. Dr. Lychik has a Bachelor of Science in Environmental Engineering from 1999 and a Master of Science in 2007 in Agricultural Sciences from the Ukrainian University of Water Management and Nature Conservation. In 2008, he was awarded a recipient of Fulbright Scholarship to pursue doctoral studies in the U.S. In 2014, Dr. Lychik received his PhD in Soil Science and Watershed Management from the University of Maryland, College Park, U.S., before joining Ag Canada, AFC's Brandon Research and Development Center as a postdoctoral fellow. Dr. Lychik assessed the interactions of agricultural inputs and cropping diversity on crop production, soil properties, and environmental quality, combined with process-based models. Dr. Lychik's work at BRDC focuses on crop production systems, climate change, and precision agriculture and field-scale modeling. Now, Dr. Moulin is a graduate of the University of Saskatchewan with a PhD in soil science. His research in AFC since 1988 at Melfort and Brandon addresses the effect of crop rotations and management on soil, carbon, and nitrogen in the context of crop rotations, management of input and diversity, and precision agriculture. He'll summarize results of an 18-year study of crop rotation and input management in the context of adaptation to climate change. There is a half a credit CEU CCA credit in crop management with this session, and I've been promised that there will be no talk of policy, that this is all adaptation and all the good stuff. So it's going to be quite an interesting session, sort of broken into 4 parts, and so there will be a little bit of back and forth between the 2 presenters. So I'll turn it over to them to get us underway. Thanks so much.
Thank you. So am I on? Well, it's great to be here. Thank you very much for the invitation to speak here. I realize it's the last presentation of the day, and so I'll try and make it worth your while for staying here. We will talk about 4 different components in this presentation, and we're going to start with crop management and adaptation to climate change. And when I talk about climate change, I'm talking about seasonal variability of weather just as much as I'm talking about climate change. And I'm going to give a few examples of that, which will help you understand what the potential is for change in the future. I'm also going to talk about my definitions of mitigation and adaptation. And as you've been told, I'm going to focus on adaptation. My role is not to talk about mitigation. We'll be talking about the diversity of crop rotation and input levels, and that's Taras. The majority of that discussion will be with Taras. I added precision agriculture because, in my opinion, and based on the research that I've done, precision agriculture has a major role in terms of dealing with seasonal changes in weather and climate change. And finally, we're going to finish with, Taras is going to finish with a presentation on field-scale research, which I think you'll find particularly interesting because it's relevant to your fields. It'll be an analysis that relates directly to what happens in your fields, and it'll give you another tool to interpret what's happening in terms of the overall agronomic management of those fields with respect to soil properties and crop yield and economic return. So mitigation basically deals with how man changes or affects climate change, and I'm not going to talk about that. I'm not going to talk about policy. I'm not an expert by any means on those topics, so I'm not going to talk about mitigation. I'm going to talk about adaptation and how producers can adapt to seasonal changes in weather, or also referred to as climate change. What the options are based on the research that we have done in field-scale research throughout the last 30 years. These seasonal changes in weather patterns are particularly obvious in the last 10 years. Those of you in the Brandon area are quite familiar with the floods that happened in 2011 and 2014. We at the Brandon Research Center also experience problems with those floods, losing plots and experimental land and having to seed later in the year. When I talk about adaptation, it's about adaptation to climate change and seasonal change. And the basic message is, the basic result of this work is, what can we do to best provide the best package for management to deal with that seasonal change? How to reduce the risk associated with that seasonal change in weather. Now, of course, one of the main questions is, well, what kind of seasonal changes in weather patterns are we looking at? Well, I can tell you right now, here's an example of the kind of change that you're probably going to see, and everyone's seen this fall, and that's unharvested fields. This is December 22nd in central Saskatchewan. This is by no means uncommon throughout the prairies and certainly is a major cause of concern. So we're going to give you some insight in terms of the research that we've done. However, with respect to unharvested crops, we're not really going to deal with that particular area. That's a separate presentation that I've given in the past. If anyone wants to talk to me about management of crop residue and unharvested crops, give me a call and we can talk about that later. So here's an example of some of the changes that are predicted for Canada. This information is in the Climate Atlas of Canada and is based on simulations of approximately 27 different climate models that are all combined in the analysis. And they show data for all over Canada, and I've extracted the data for Brandon. So this is the change in temperature for mean annual temperature for the period from 2021 to 2050 compared to the previous period from 1976 to 2005. And this is the comparison I'll be referring to in all of these slides. So this represents a change of about 2 degrees, a little more than 2 degrees C for mean annual temperature. And that doesn't seem like a lot. However, when you break it down and you look at it in terms of seasons, it does mean a lot, particularly with respect to precipitation. And warm days. Here's a prediction for the change from the 76 to 2005 to the second period in the future, 14.6 days compared to 30.6. So the prediction is based on these models, and this is a lot of scientific research has been done. This isn't just one scientist producing one set of data. It shows there's going to be a lot more hotter days during the summer. And you can appreciate the consequences in terms of crops, such as canola, which is affected by very hot days in July and August, and the effect on flowering. Annual precipitation is going to change with a difference of about 30 millimeters. That might not seem like a lot, but when you take a look at spring precipitation, that's where you look at the seasonal component of climate change. The seasonal component, you'll see that we're looking at more precipitation in the spring from 118 to 131 millimeters. Well, what does that mean? Well, in the spring, the soil is probably frozen or saturated with water. So that's going to have a lot of consequences, more so than the overall precipitation over the year, but more so in the spring, and the consequences for seeding and the consequences for spring management. Fall precipitation is also predicted to go up from 104 to 112. Obviously, this year was an anomaly and much more than that, but the overall prediction is for an increase in fall precipitation. When you look at summer precipitation, it's basically the same, only 2 millimeters. So not a real big change during the summer, it's the change in spring and the fall. Heavy precipitation days are also going to increase by about 0.5 days, but a heavy precipitation day certainly has a lot more impact in terms of that actual day, as you can all well appreciate. So that gives you a background in terms of the seasonal weather changes, albeit climate change, that we're going to be looking at. And now Taras is going to talk about the results of a long-term research project that we conducted at Scott, Saskatchewan. It started in 1994. Taras is going to give you the details. And I guess the key point is that when Taras describes the results of that research, pay attention to the variability in that 18 years of data. It's very interesting information and quite useful in terms of looking at the potential for management under climate change and seasonal changes in weather. Taras.
Yeah. Was this on? Okay. Thank you. Hi, everybody. Thank you very much for your time and interest in this presentation, and thank you, Alan, for the introduction. Going to talk to you about this this long-term rotation field study that was implemented at a research site in northwestern Saskatchewan here. And just a few words about this study. This is one of the unique studies, not only in North America, but in the entire world. There is only maybe 24 of those that have resulted in such a valuable data set of information with regards to crop yield, nutrient data, and soil properties data. And this is just so you understand how labor intensive it is. For 18 years, there was a full-time staff on the farm in Scott who did the research, the field operations from 8 till 5 every day in the spring or the summer. And they were there was somebody working on collecting data, measuring all the, doing all the soil sampling, processing sample, analyzing samples. So over 18 years, it was over $5 million that were spent on that study. Just so that you understand the scale of this. And as I said, this is the location of the study. It's in the dark brown Chernozem area of the Canadian prairies, coarse, loamy textured soil. Now this is the aerial view of the study, and the scale of this is the entire study took 16 hectares. Each of these plots is 40 meters long by 13 meters wide. So just so you understand how big of a project it was. And it ran from 1994. The last year of the study was 2013. So there were 3 full 6-year cycles of the study. And so basically the overall goal of this study was to replicate the typical practices in terms of inputs or tillage intensities intersected with different cropping rotations. And the idea was to find that ideal one or the best one that works for better crop yield, higher nutrient contents in that crop, less environmental impact in terms of nutrient leaving the field, better soil properties, building up of the organic matter. So those ideas were behind that study. And so there are 3 levels of inputs that are listed here and 3 levels of diversity. So there was organic input, which was which had no chemical, no herbicide and pesticides, and tillage was used for weed control. Reduced input was where pests and nutrients were managed in a minimum to no-till system with target yields and soil test recommendations. and they were based on integrated long-term management of pests and nutrients. And the high input or conventional, they were, this is where pesticides were used as required and fertilizer were used as required with tillage. Now, in terms of the cropping diversity, there were also 3 levels. The low crop diversity was a combination of wheat, oilseed, and fallow or green manure-based rotations. The diversified annual grains was they had wheat, barley, fall rye, or diverse cereal, oilseed, and pulse crops. And diversified annual and perennial crops were a mix of grain and forage crops, mustard, wheat, barley, alfalfa, canola as well. So I had a little bit of a background. I came to Canada in 2014 as a postdoc, and I had this massive data set of yield and soil N and P data that I had to analyze. And we've published 4 papers so far on that particular study. There is a 5th one that is going to be submitted soon. So I had to be really, I couldn't put a lot of the information in that presentation in the interest of time. But I just selected a few that are most appealing, that I thought would be most appealing to the audience. So, in this type of research, when we introduce what we call fixed treatments, or the treatments that we have control over, we typically then collect the data and we run statistical software to analyze, to see to see what we call a response, okay, from these field treatments. However, there are also other factors that affect yield in this particular case. And I'm not going to talk about nutrients here, but they're also important. So these factors are seasonal variance, basically the precipitation and temperature, or seasonal variability of both. There are also spatial trains due to drainage, soil texture, and organic matter, and of course the management of crop inputs and rotation, what I refer to as fixed treatments. So what you see here is the diagram of the wheat yield over the long term. The last set of bars here shows the wheat yield across all years, and you can see that the yield in high or conventional system and reduced, they outperform wheat in the organic system. And you can see that when broken down by the cycles, these are 6-year cycle averages, there is a great deal of variation in yield. And you see again in the first cycle and in the second cycle, the yield in the high and reduced systems are outperforming organic. So this is the same diagram that you just saw, and with this one, this is when we also put the rotation or the diversity levels in the picture. Again, these are the 3 cycles and the long-term average, the 18 years. And this is a growing season precipitation graph, which Al was referring to, that might be interesting for you. So you can see that throughout the study, there was a great deal of variation in precipitation. The first 6 years were dry. The last 6 years were wet, and there was the 6 year in the middle were in the middle. This year here, 2011, I believe, this was the wettest year since 1903 at that location. And that certainly affected yield, in our opinion. Now, when you look at this pattern and you compare this pattern, you see some similarities, right? So that was our idea when we put this information in a statistical analysis, and we used, in this particular case, we use these days are considered the data of like a big data or analytics. We use partition analysis and partial least squares. And what it does, it basically, when we put those factors in the statistical model, it tells us how much variation in yield were introduced by that particular factor, and if there is an interaction between the factors. So after we ran this analysis, we found out that monthly growing precipitation, growing season precipitation in April, and growing degree days in June and in July were key variables for wheat yield in that particular study. So further to that, there was a variation. There was a variation that it was never driven by the fixed effects or the whether the tillage or cropping rotation on the long-term average. There was an effect, but it wasn't as big as we expected it to be. So, and you remember this diagram that I've shown you, the 1998 year, the driest year in the study. In that particular year, where's my slide here? In that particular year, approximately 50% of variation in yield was attributed to input and diversity. Basically, the half variation of yield was explained by input and diversity, but the remaining half was explained by other factors. In 2006, this year, input and diversity, the fixed treatments that we introduced in the field didn't account for any variation. It was all related to precipitation or temperature. In 2010, the wettest year of the study, about 2/3 of variation in the yield were attributed to input and diversity, with remaining yield variation due to drainage. Now, so this I can made a slide with conclusions here that precipitation and soil moisture were key factors in this long-term rotation study, and important message here is that had we not included those factors in the analysis, we would assign the differences in yield due to either inputs or tillage intensity or rotations, or the two factors combined if there was an interaction. So the fact that we included that information in the analysis shed light on something that we didn't know before. So in this particular case, yield was affected by a combination of input terrain attributes, which I'm going to talk about more in the second part of my presentation, growing season precipitation and temperature, and cropping diversity depending on precipitation and temperature during the year. So the next step in this research was to validate a process-based model called the Environmental Policy Integrated Climate Model with the experimental data that we had accumulated over 18 years of that study. And what process-based model is it's a simulation model that is run on a computer, which takes all the information from the field in terms of field operation, implements, planting dates, harvesting dates, the rates of fertilizer, the types of fertilizer, the depth of the application of the fertilizer, it's a complete biophysical and biochemical model. And what I mean by that it takes the processes in the model. These processes are connected to each other. So, for example, if there is a particular implement that will compact the soil, it will affect the bulk density, which will affect the aeration, which will affect the moisture distribution, which in turn will affect the nitrogen distribution in the field. So whatever you do in the field will be also reproduced in that model. And when we work with models, we typically do what we call calibration. And basically, this is a jargon for saying to see how well the model represents something that already happened in the field. And because, and again, going back to that study, this is one of the unique studies where every single piece of information over 18 years, what happened in that site was recorded. So it took me 3 months actually over the first summer in 2014 to encode that exact information with exact dates and specific implements into the model. And then I ran the model, and then calibration is basically then assessing how well it reproduced something that already happened in the past. And because we had this yield data measured, we had those N and P numbers there, we could then run the analysis to assess how well that, how close the match was. And you've probably seen that this model takes a fairly robust set of information in terms of weather, in terms of soils, in terms of operation. As I said, it's very detailed, and it's a daily time step. So from the output, it's possible to assess how well that model performed. And now, when it comes to see what we did later, we successfully validated, calibrated, and validated the model. And then what we did, the idea here was, if the model does something that happened in the past successfully, that we input the new weather information in the model. In theory, it should accurately reproduce the changes in yield or changes in soil nutrients into the future. And for that particular exercise, we used the product from a research hub at the University of Colorado. And this stands for North American Regional Climate Change Assessment Program. It's been around for quite a number of years, and their approach is quite unique because their data is also downscaled to regional scale. They run it with regional climate models, which have less degree of uncertainty compared to global climate model. And it takes this information takes six variables: maximum and minimum temperature, precipitation, solar radiation, wind speed, and relative humidity. And it all, depending on the parameter, some of those are measured as often as once every 3 hours. But the model has a daily step, so it's a daily step model, which is also quite unique compared to other models available there. So when we overlaid that new climate scenarios over the 30 years, beginning of 2041, we saw these changes in the production of these three crops. Now, all these crops are C3 crops. Okay, so they're quite sensitive to the increase in the ambient CO2 concentration because they are due to CO2 fertilization effect. However, we took one step further with that, which, as I said, we broke down this new the variability in seasonal weather to two main components: the changes in growing season precipitation, changes in growing degree days. And in the future, we're also going to introduce a new factor of a annual increase in CO2 concentration. So we were able to break down that signal and assess the effects from each of those factors into the future, which I'm going to talk about briefly in a couple of minutes. But you see that all crops are projected to increase, and in case of barley and canola, these increases were higher than other systems, but not significant. However, in terms of wheat, the increase was significantly higher than the one grown in the organic system. So some conclusion there are that the crop yield will be affected due to increases in precipitation, growing degree days, input management and diversity, and terrain attributes, which I will also discuss terrain attributes more in details. Well, Alan will do that first, and then I'll continue. But the other slides, I said there was too much information. In terms of wheat, for wheat, the precipitation and degree days, in many cases, they accounted for more than 1/3 of the variation in the future projected yield. For that particular location in Scott, the maximum and minimum growing season temperature will increase by a little over 1 degree and 2.03 degree for minimum temperature compared to historical normals in Scott, and growing season precipitation will increase by as much as 11%. Now, the other slides that I haven't shown you has to do with nitrogen and phosphorus. And there we run the analysis, and it's for yield and nitrogen and phosphorus, the conclusion that we made was that adoption of reduced input-based system might be beneficial and may provide producers with an adaptive strategy for climate change. Again, I wish I could present you more of the numbers, but in the interest of time, I guess I have to move on. And in addition to those factors, the cropping diversity, the diverse annual grain rotations were also shown that they are better in terms of future projected yield, and also they tended to be ones that had less nitrogen leached from the field because they tend to uptake more nitrogen, grain crops. So for these reasons, it was concluded that the reduced inputs with diverse annual grains might be an option for producers to consider in light of these seasonal variations, projected seasonal variations in weather at that particular site. And yes, so this is where, Al, I give you a floor again.
Thank you, Taras. Just to review a couple important points that Taras made. One was the importance of the input and diversity combination in the dry period, in that dry phase, the first dry phase that started in 1998, and the very wet phase. Those two particular wet phases were best managed by that combination of input and diversity, which was the reduced diverse annual grain system. Right, one key aspect that Taras emphasized was the importance of soil test, which was a key aspect of the reduced input management. So it's important to conclude from those data and this study that reduced input system combined with a diverse annual grain system was the best suited for that very dry and that very wet environment in that particular study. And I think the results of that research applies across Western Canada as well. As I was preparing my presentation and realized that I'd be dwelling on the importance of soil test, I couldn't help but think of some other research that I've done in precision agriculture and the variable management of nitrogen in canola. So I'm going to spend some time talking about that. It's another means of dealing with seasonal variability in weather, as you'll see from my presentation. So the questions that producers posed when I started this study were, does precision agriculture work at the field scale? Field scale is a key question from the producer's perspective, as is economic return. What are the environmental advantages to precision agriculture? And finally, does precision agriculture address the year-to-year variability of yield? This research started with work at the Manitoba Zero Tillage Research Farm in 2002 to 2008. We compiled data from 2004 to 2008 in the analysis of yield maps at that site. And we also did some field scale work in 2013 and 2015 at the Manitoba Zero Tillage Research Association Farm. And in 2014, we started a study funded by the Canola Council of Canada and Agriculture and Agri-Food Canada on, from 2014 to 2017. It's a comprehensive, large-scale, field-scale project, 26 site years of data on farms in Alberta, Saskatchewan, and Manitoba. The research was done with farmers' equipment. All these farmers had precision ag equipment designed to apply precision, vary the rate of nitrogen applied at the time of seeding with canola. And they also had yield data, which we used to develop the yield zones. These are the sites that I referred to. The sites were located in a group near Lethbridge, a group near Melfort, a group near Morden, and one here just south of Somerset near. We measured a number of variables of interest at the field scale, including canola yield. We measured canola yield with yield monitors. We measured landform and terrain attributes, which were calculated from the elevation data collected with the yield monitors. We developed management zones based on analysis of historical yield data, 3 to 5 years of yield maps that were combined in a statistical analysis to identify where the low, average, and high-yielding zones were. And we varied the nitrogen fertilizer rates. We used field-scale research with producers' equipment. I can't stress that enough. The research at the zero-till farm and the data in this particular project were all done at the field scale. So this is certainly a significant component of research that is done in Agriculture and Agri-Food Canada. Those of you who are knowledgeable about precision agriculture realize that there's a lot of variability, and we've attempted to measure as much as we can in terms of this variability and to account for it in terms of the variability of yield in the zones, the yield map accuracy, yield outliers, the alignment of GPS points. We assessed all the GPS data to ensure that it was as accurate as possible. Many of our producers have RTK systems. We assessed the calculation of yield position to minimize the effects of grain residence in the combine. We normalized the crop in the analysis of multiple years. That is, you can't directly compare flax production with wheat production in terms of tons per hectare or bushels per acre. You have to normalize those data so they're comparable and useful in the analysis. We also had to assess the various systems that were used by the different producers. Some of them used multiple combines, and we had to make sure that that was comparable. We used weigh wagons and commercial scales to ensure that the yield monitors were accurate, working properly. And finally, we did extensive campaign to measure soil property throughout all of the fields. We delineated the field zones of high, average, and low with commercially available software, which is SMS Advanced Software. And we used a procedure called cluster analysis, which goes through all of the data for those 3 to 5 years of historical yield data, and it combines them into 3 zones. Now, I've designed the experiments so that we had 3 zones. There are other options for up to 10 zones, and some companies use 10 zones. I wanted to make sure that we had the 2 extremes plus a midpoint, which producers could relate to. In addition, the average zone was what the producers were planning for in their overall field management. Those terrain attributes, that elevation analysis, we calculated 49 different measurements of terrain variability, from the low points to the high points, the slope, the aspect, quite a few different variables that we're trying to assess and use those data to account for some of the variability in the crop yield and soil nutrient uptake. This is an example of the yield zones that we calculated for one of our fields. The green is the high yielding area, the average is the yellow, and the red is the low-yielding areas. Now, you can see that the headlands in this field, as in many of these fields, are low-yielding, and they're a result of a number of factors, so we didn't locate any of our plots in the headlands. Those factors could include salinity due to impeded drainage, compaction, overseeding, or issues with respect to the yield monitor not collecting sufficient data when it's turning around in the headlands. The treatments for fertilizer were 0, 50, and 100, and 150% of nitrogen based on soil test. In other words, we measured soil test in the fall or spring prior to seeding, and we calculated fertilizer nitrogen rates based on those soil tests and the targets that the producer identified for that field. Now, many of these targets were their historical average or their average yield over those 3 to 5 years, and they usually were around 50 bushels. Now, when we designed the experiment, we nested the fertilizer treatments within the yield zones with 4 replicates, and we had a control. I want to emphasize, we had a control, so we know if the fertilizer had an impact or not. That's a key factor in a rigorous scientific study. This is one of the sites where we did this study at the Zero Till farm north of Brandon, and you can see the long strips. These strips are about 20 meters wide, 20 to 30 meters wide, and about 100 meters long. So they're done with field scale equipment of the type that producers would use. These are a couple other sites in our study. This is one site in Manitoba. We designed the experiment to go across the low, average, and high zones with the 4 rates of fertilizer. Now, these fertilizer rates are based on the calculations from the Manitoba Agriculture and Food. Manitoba Agriculture and Food have done a good job in developing fertilizer recommendations for hybrid canolas, and certainly we wanted to use the best available recommendations in the study. Here's another example, and you can see how the treatments are spread across the field. They're away from the headlands, in the center of the field, across the different zones. All of these were done, I want to repeat that, with field scale equipment by the producers. Most of the fertilizer was applied at the time of seeding, mostly with urea. There were a few that used liquid nitrogen during the growing season, but that was a minority of the sites. I've touched on a number of these points already. The yield goals are set by the producers for each field. Now, when we looked at those yield goals for the average treatment, that is what the producer would normally do, we adjusted that yield goal for the high yielding zone and increased it by 10%. In other words, the yield goal for the high yielding zone was higher by about 10%. It varied a little bit between producers. And for the low producing zone, we reduced the yield goal. In other words, if the yield goal was 50% for average, it might be 45 for the low and 55 for the high. So we adjusted those yield goals to account for that variability in the historical yield for those zones. Now, one of the questions that always comes up in my presentations is how about potassium, phosphorus, and sulfur? We applied in all of these studies sufficient potassium, sulfur, and phosphorus to account for the variability in yield that we expected in all of these treatments. So we determined, based on our analysis of soil test plus the fertilizer rates that the producers used, that PK and S were not limiting factors in the study. The only limiting factor in the design was nitrogen fertilizer. This is the growing season precipitation for the provinces in 2014, 15, and 16, and you can see they're relatively uniform, except Alberta had a very dry year in 2015. And relatively uniform growing degree days across those 3 years of the study. I don't have 2017 in this figure. Now, I presented these data to 5 or 6 different producer organizations, and I had maybe a dozen slides. But that's far too much information for today. So I've encapsulated all the results in this one slide. And in this slide, you can see a number of trends. First, this is the low zone. That's that low producing zone. This is the average producing zone, and this is the high producing zone. And you can see clearly in the high producing zones for those 26 sites in the 4 years of the study that those high producing zones are producing much more than those low producing zones. And of course, the average is in the middle. The second point is that those controls have significant production. Even in the low producing zone, we've got almost over 2 tons per hectare of canola in those low producing zones with a low rate of nitrogen fertilizer. And that's an important point which I'm going to address a little bit later. And as you compare the inherent, so I would attribute that as to the inherent fertility of these different zones. And you can see that this low zone on the left, the control is at 2 tons. You go to the average zone, the inherent fertility is higher. And you look at the inherent fertility in the high producing zone. So obviously there's a difference in inherent fertility across all those farms between those zones. So we've certainly got a definite trend in terms of the relative production in the zones. Now that's probably a function of other factors, and I have to stress that there's a lot of variability between farms. In some farms, there's very little. This trend is very, very low. In other farms, it's quite evident. So there's a lot of variability between farms, and that's a function of historical management and residual nitrogen and organic matter and soil properties. As you saw from the previous slide, we looked at a lot of different sites across Western Canada. The other point I wanted to make was you look at the fertilizer response. In the low zone at 100 and 150, not a lot of difference. But importantly, in the average, at the 100% are recommended, based on the Manitoba recommendations, we got the best yield on the average and in the high. So that fertilizer recommendation from Manitoba Agriculture and Food appears to be working. If you use those high rates, you're getting less production at 150%. Of the recommended in the average and the high. Now this is based on an analysis. It's a more complex statistical analysis than I've used in the past. Some of you attended some of my presentations in the past will see the amount of variability. I used a different analysis, and it used all of the data points that we collected in this study. There are over 13,000 data points that go towards this analysis. When I use the statistical power of all of that data, that's the result that I get. And that's the important message. Now, what does this mean in terms of seasonal variability of weather? Well, obviously, these high zones and these average zones are producing more than the low zones. One of the key factors we've observed is that those low zones are often in the lower slope positions where there's salinity or excess moisture. Salinity or drought, conversely drought, is certainly key factors. But on average, when you're looking at the average yielding zones and the high yielding zones, over time, those are relatively higher than the low zones. So what does that mean in terms of seasonal weather change? Well, if a producer is to optimize for seasonal changes in weather and optimizing for the incidence of excess moisture or perhaps drought, maybe they want to focus their inputs and their bang for their buck with their new fertilizer on those average and high producing zones and manage those low producing zones differently. Don't spend money where you're not making money. We've done economic analysis on a subset of 12 sites. We weren't able to get all of the economic data we needed for all of the 26 sites. And in that analysis, the high yielding zones yielded more and provided more income than the low zones. When you compare this management across the entire field of variable management, it's you use about 7 to 10% less of nitrogen fertilizer in the variable management compared to uniform management. Yield and economic return in the low zones is more at risk due to seasonal variability of weather. And as I mentioned, economic return by managing the low zones might be an option in terms of dealing with seasonal variability of weather. So the next stage, coming from this research and all of that variability that we've looked at in the field, is field scale research. And this is research that for us is going to continue in Agriculture and Agri-Food Canada, and it's going to give us even more information and a better opportunity to assess field scale processes and field scale response to fertilizer management, to tillage management, in the context of not only yield, but other processes like soil erosion due to wind and water. So, Taras?
Yeah. Hello? 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 Is it working? Hello? Yep. Okay. Sorry, I didn't realize we are over time now. I saw we have until 4:15, so I'll try to keep it short. So the sites that Alan was referring to, the 24 fields across Western Canada, we are integrating those sites in the field scale research with the different product that derived from the EPIC model. It's called the ARC Apex, which I will talk to in a second. But the objectives in this project are to assess within field variability of wheat and canola with respect to fertilizer management, crop and residue management, and simulate yield, economic return, and hydrology, and also overlay those new actually they're even further scaled down climate change scenarios on the regional scale in fields with variable rate of fertilizer application. So the idea here is to take as much information from those fields and input them into the model and overlay those prescription maps along with the concept of production zone management with low, medium, and high production zones. Of course, validate and calibrate and validate the model, and then assess the effects of further changes in weather parameters into how certain practices will or will not be sustainable into the future, and most importantly, how those production zones will act in the future. So a few words about that model that I was referring to. It's called the ARC Apex, and its ARC is referring to the ARC that it's you can run it through ArcGIS platform. And this model is the engine is basically coming from EPIC, the model that I was talking about before. The important distinction of this model is that this model breaks down the field into individual so-called hydrological response units, which are homogeneous subareas of soils based on soils, land use, and topography. And this model simulates the flow, or it routes hydrology from one sub-area to another through channels and floodplains, and it simulates the movement of sediment, nutrients, and pesticides. And of course, it takes into account all those biophysical and biochemical processes that I was talking about. So this is how one of the fields that of one of the producer from Manitoba that part of this project. This is the field that's broken down on those hydrological response units, so we can assess with that model edge of field losses of N and P, for example, for the entire field or for each of those individual, you can call them mini watershed or hydrological response units. And it takes into consideration all the detailed microtopography with regards to slope, with regards to micro elevation or mini depressions. Like, for example, this one is a % slope in that field shown. Now, what we do then is we overlay these yield maps with the information that we have from those fields, and this again, this without and with crop yield map information over it, and this one is just the pure broken down field on those small hydrological response units. And we can the idea here is to take into account as many layers of information as we can with regards to field management, the operations, the exact fertilizer application rates, and then we look at the long-term yield projections, and then we can tell farmer that these areas are producing consistently low yields, and then we can tell why. We can tell the factors that are affecting the yield or N and P losses from those areas, and we can then suggest alternative practices, what can be changed in those particular sections of the field based on the yield driving factors that we identify. So this is just to show you some additional information that we take into consideration. We look at the detailed topography, soil. This one is the detailed wetness index. So this is the moisture distribution in the field, which will affect nutrients and crop yield, which we take into consideration, and then we can enter this information in the model. We can run it and then assess the output. In addition to that, we're also creating profit loss maps, which is of particular importance for producer. So we can say which, as I said, which areas in the field are consistently yielding higher or lower, and which factors are responsible for that, and what can be done about that. And these are the last three slides, some of the outputs that this model can produce. Again, it goes either on a whole scale field, or we can run it based on those individual hydrological response units. And this takes into consideration information that Alan was talking about, the production zones, because we know the inputs there, and we can overlay the future projections in climate. We can predict how these production zones will high zone continue to be high 30 years along the road, or no, or will low producing zone continue to be low producing zone, and so on. So this one shows you the output for projected yield. This is for water erosion, and this one is from wind erosion. Yeah, I think that was the last slide. So wanted to acknowledge people. Without their input, this research wouldn't be possible. Arnie Waddell and Andrew Kupichuk, our technician. I believe Andrew is in the room here. Yeah, thanks a lot. Steve Sager and Rejan Picard. Rejan, is he here? Yeah, he was. They were essential for this research. Staff at Scott Research Farm, Arlen and Larry, Ross, and as I said, my postdoctoral studies were, when I started, were funded by AFC Growing Forward 2, and I also would like to recognize the funding from AFC Lake Winnipeg project. And sorry, I'm over time. I didn't realize. I know if we have time for questions, or we'd be happy to answer any questions. Yeah.
We had a miscommunication as to whether we were 4 o'clock or 4:15 as an end time. So I apologize for any confusions there, depending on which agenda you were looking at. But is there any questions in the room? Yes, we've got a question.
Well, Wayne here just indicated, Al, that this is your last official day of work.
Yes.
Congratulations. I do have a question, though. In the information you indicated that we're looking at 30 plus days above a certain temperature in the future. If that changes to 40 days or 50 days in that period, is your software capable of responding to those changes? Like, and this is from a greenhorn. Do you understand?
Actually, that's a question that a scientist would ask of any modeler. Is that range outside the box of the model? And that's a good point. These models are fairly flexible. They're designed based on the physical processes and the biological process related to crop growth. They account, as Taras pointed out, for the effects of CO2 enrichment and the changes in precipitation and the changes in temperature. That said, the models for simulating soil processes, water movement, crop yield are really going to be pushed when we start talking about 30 days of very hot weather in the summer compared to 14 or 15. But it's the best information we have. This is also the best information we have when we're assessing things like tile drainage. Tile drainage seems to be a pretty important consideration and discussion point these days in terms of dealing with excess water. This model allows you to actually identify those areas in the field where you're going to put your tile drainage and assess what the consequences of that tile drainage are going to be. Other options that you can use with this model, and it's at the field scale, so you're looking at that one field, a quarter section or a half section, and you're going to be able to see on the field what the consequence is of, say, of tile drainage, or of a different tillage system, increasing the number of tillage operations, and the consequence for crop yield and soil properties. So it's going to give us a whole new level of detail and a whole new ability to analyze the data in terms at the field scale. That said, going back to your original question, this is certainly pushing the realm of the model. We really don't have data to confirm these calculations. It's based on physical and biological processes. It's the best information we have. So that's the context for our analysis and the information that we're providing to producers. I hope I answered your question, Wayne.
Any other quick questions? Okay, this will be the final one, and then we'll wrap her up.
Great presentation. Glenn Friesen here. Question on sort of related to what Wayne was asking. If in what you're suggesting is the model is based on the data you have. But if you had access to all of the production data in Manitoba that maybe volunteered from producers, and you had the rotations, you had the practices, would that create more validation for your model and more applicability or reliability in it?
Yeah.
Go ahead.
Was it a question for Al or for? Well, I can address that.
Go ahead.
Certainly, the more detailed data, the better. Like this model, if we input what we could have done, like we could have really simplified our lives and take information from Manitoba Fertility Guide with regards to fertilizer rates and applications, and based on the crop, we could have taken unified data for based on the different region on the province. But then when we make recommendations to producers out of it, they're less applicable. That's why we go to field scale and we work with exact producers, because then we relate this information to their particular needs and fields. And we could have, this is quite distinct from running with other models like SWOT that would simulate the typical production in the entire Western Canada. But then when it comes down to producer in Carmen area or in Moulin, where the moisture situation is different than in the rest of the province, then these people keep wondering how it applies to their particular fields, that general set of recommendations from that big output model that simulated the results for Western Canada, which I'm not saying is not useful. It's useful information. But if we wanted to go on a specific scale for a producer, we believe that this particular approach, with as much detailed information, we're talking about reproducing the exact depths of the application. It's not. I'm not aware of any other product available there, and Al is quite picky about models, if you ask me.
Yeah. I'll take just a few more minutes, if you don't mind. Just to address your question, we'd love to have a lot of data from other producers. The Canola Council gave us one of the best opportunities ever to do this type of analysis. But I collected an awful lot of data for these fields. We have soil properties, all of the soil test analyses, soil texture, EC, pH, cation exchange capacity, at a number of different depths throughout the field, soil organic matter. So we have a lot of data which those producers may not have, but we can collect whatever data they have and see if it works with the model. That would be the first step. But I want to emphasize the one key component of the Canola Council approach, Canola Council project approach, was the analysis of yield data and historical yield data. And I believe there's only 10 to 15% of producers who are collecting those yield data that we could actually use. That's going to increase in the future as producers become familiar with the technology and have access to the technology. But that's a key component of this analysis and is very important in terms of interpreting the analysis, the simulations. I hope I've answered your question.
All right. Thank you, gentlemen. One more round of applause for both of them for taking the time to explain this model to us.